Hello, everybody. This is John Berry again for the monthly AIPG Texas webinar. And this month we have Phil Orlandini, uh, who is going to speak about a very deep shear zone in northern Canada and evidence for brittle deformation at extraordinary depths. Phil has a PhD from CSM and has worked for the Bureau of Economic Geology in Austin. And he's, as I say, he's going to give this talk on laboratory for mixed brittle and ductile deformation in the continental lower crust. Go ahead, Phil.
Well, thank you, John. And thank you to all the members of the AIPG to make this possible. I'm really happy to be here sharing this with you guys. I've taken, not to summarize John too much, but sort of a weird path into geology to get my PhD. Then ended up working at UT for a while as part of the microanalysis laboratory there. And then now I'm actually not really in geology at all anymore. And instead, I work for a software company as a data scientist. So I'm trying to keep my love for geology alive. Hopefully, I can make it to the field trip that I just heard about is Saturday morning. That would be pretty cool. But until then, I'd love to talk to you guys about what I did my PhD on. And most of my research, when I was in academia, focused on the interplay between brittle and ductile deformation because I just loved crystallography. I loved like the chemistry of it. I love metamorphic petrology, and you find all those things in a really rich intersection when you think about the way that rocks deform at high temperature, whether they're flowing plastically or sometimes failing brittly, which is sort of the exception to the rule. And so this picture that I put here is not just eye candy. This is an example of the field area I'm going to be spending all this time telling you about. It's called the Cora Lake Shear Zone, and we'll get into more details later. But it's essentially this exposure in northern Saskatchewan of deep, deep continental crust. And you can see it's very finely lamellar. You can see it's strongly segregated into, the sort of white bands and the dark bands. And this is what's called the Chipman tonalite. And it's really, really old and came from really, really deep. And this is about half of the shear zone we're going to be talking about in more detail. And one of the cool things about this, because it's really fun to talk about fieldwork usually, is you can see that this is all these like glacial hillocks because you're so far north that the ice sheet has done a lot of like job polishing off these outcrops for you. But you have to wait for a forest fire to clear everything away from you. And you get these beautiful flowers that grow when it's roughly the right time that it's worth taking a float plane in to like really explore the region. And you're not just dealing with, like moss and loam the whole time. It's pretty difficult to do this field work when there hasn't been a burn in the last decade or so. So we will move along. Okay, so this term natural laboratory, it's something I picked up because it, theoretically helps you get funding, but it is a cool concept in general, right? To make sure that your academic research doesn't get too academic. And so we like this idea of a natural laboratory, as John would say, because it lets you really appreciate the complexity of like the sort of problems that we encounter as natural scientists. So it needs to be like well exposed, well preserved, and it just gives you the full barrel. Like, I do not know what I am seeing right now. And my God, if I go 200 meters that way, I really don't know what's going on because that's when you really get to learn some cool stuff. And so the Cora Lake Shear Zone is a good example of this. And so in our case, our natural laboratory is in the lower crust. And so its complexity allows you to look at all sorts of cool interplaying processes. You can think about questions like, what is the strength of the lithospheric crust? Traditionally, the easy assumption is that it's real hot, it's quartz dominated, and so it's real weak, and it doesn't really sustain differential stresses. You can look at passive properties of ductile deformation that could be visible from the surface. This would be sort of like the alignment of seismic waves due to crystallographics orientations, all sharing the same sort of orientation within a very many kilometer zone. You can look at general patterns of alignment in crystals for the deformed rocks or the absence of patterns. Sometimes they compete with each other. That can be really cool. And then, of course, you have like all the metamorphic reactions that are the bread and butter of a typical sort of metamorphic petrology study because you've got fluids running around down there. You've got melt. You've got the minerals exchanging things with each other. It's great. It's a total party. So what we're going to be focusing on for this talk is just the question of strength. How strong is a lithospheric crust? Because that assumption plays into a lot of assumptions we make about the strength of the crust in the upper crust, which is what we really care about because that's where we get earthquakes. Earthquakes actually impact our lives. So into this question of why should anybody care about this academic research project. So here's a cute little cartoon that I shamelessly stole from Aiming Lin, which of course includes the catfish at the center of the Earth that is the source of all earthquakes ultimately. But it's a really good generalized cartoon for how we understand the strength of the crust. So at the top, it's cold, you're above like 10, 15 kilometers. And for a quartz-dominated lithology, that is brittle, right? If you put a shear stress on that thing, it holds on to it elastically until it goes. Then you have this sort of messy sort of transition zone between like 10, 15, 20-ish kilometers, where because, the temperature increases, your quartz-dominated lithologies start to behave more and more crystal plastically and therefore ductilely than brittly. So you start putting a differential stress on those puppies at that depth, and it's like, well, they don't just hold on to it, right? They flow with it a bit. And then below like 20-ish kilometers, you're just like, all right, well, it's real hot. All the quartz is flowing. So basically the whole rock is flowing. And so the rocks at that depth don't hold on to any of the stress that you give them. They just flow in a ductile fashion. So this has led to the rise of like the general assumption that like earthquakes, you'd expect to find them 15 kilometers and up, with the exception of like some really weird circumstances, maybe involving mantle lithologies or something. And this is generally true. It's a really useful general conceptualization that you'd find in a lot of like introductory geology classes. But because some people need to do PhD theses, it's always good to look for the exceptions to these sorts of generalizations. And so when you do start poking around, there are lots of examples of seismicity that occurs in the crust, or at least what we think is the crust, probably, right? That is much deeper than this assumption would have you believe. And so here's just one summary figure from not even a particularly recent paper, looking at a lot of these earthquakes that occur, and you can just watch occur, that are happening much deeper than they really should. And so it raises all sorts of interesting questions, right? Is this like a stress regime thing? Is this strike slip versus, normal or thrust faulting? Is that the thing? Or maybe you just have some weird lithologies down there. It could be any of that stuff. But the fact remains that the seismicity does happen deeper than it should, right? According to this general conceptualization. And so it's an interesting thing to sort of investigate. And so one of the ways that we looked at this, right, is not being seismologists, God forbid, real geologists. We wanted to know what such a deep seismic event would actually look like in the rock record, right? Not just some, red-blue map showing that something happened where we can't see it. So the way that we're going to sort of pitch this whole thing, right, to try and keep people's interest and following along and so you guys learn something, is first of all, like, how do you even know that you have a problem that's worth investigating, right? This is not blue sky science. We're not going to do this just because it's there to be done. And so we're going to talk about what a frictional melt is and why it's evidence for seismicity. And then we're going to talk about how you can establish that this rupture, this seismic event that you have a rock record of in the form of a frictional melt actually did happen at a deep enough depth that it qualifies as potentially being like a fossil deep earthquake. And so then, once we've established that we probably do have evidence of deep seismicity in the rock record that we're looking at, then we got to think about why. Why does this thing snub this otherwise very sensible rule, talking about, the rheology of quartz-dominated lithologies, that is generally true at predicting the mechanical behavior of the crust? And how can we tell if that's happening today in those in the seismic events that we can currently observe without being able to see the rock record of them? And so that way we tie it all back together as like, okay, here's the rock record of a cool seismic thing we can actually observe and marry the two. So here's the more complicated version of this roadmap, and you're not going to be quizzed on this, so don't worry about it. But generally the flow of our logic is going to take two parallel paths, and I'll walk you through them one at a time, and will result in tying it all back together. So the first thing, what the hell is a pseudotactylite, right? It's probably one of the worst named rock types in all of geology. And so maybe this will work, maybe it won't. This is a very cool video. You're going to break the machine. Stop. So what that was is it's two like donuts of basalt that they, milled roughly into shape, and you have this high velocity frictional rotation device, right? That I think was repurposed as a frictional welder. And they ground those two puppies against each other at seismic slip rates to see what would happen. And big surprise, there is a ton of, first of all, comminution, right? So surface areas get like super, super, super high as you produce a ton of rock flour in the first instant. And then frictional heat goes crazy, and you end up with this flash melt that goes spewing out the sides of this extremely awesome machine. So that's a pseudotactylite. It's a frictional melt as a result of seismic slip rates. Now, can I advance my slide? I can't. Okay, so great. So that's what it looks like at an experimental rock deformation apparatus in Rome. This is what it looks like in the rock record, because this is constrained, right? With the Shiva instrument, the melt could just go flying off and like scald some undergrads, right? But here in the real rock record, it's all pressurized. You know, the melt doesn't really have anywhere to go. And you end up with a lot of textures that look like these sort of dark colored breccias. And the breccias will have these little like injection veins because you have this volumetric problem when you're doing this in a real rock. And so you have shattered bits of the host rock. You have the quenched melt, which can look a lot of different ways, and we're going to go through that, especially in a metamorphic environment. And then you have these little injection veins that pop off at right angles to that. Not that they necessarily stay at right angles when you're in a ductile environment, but this is what a pseudotactylite looks like. If you guys have ever seen anything like this, you should write it down. You should send this in, because pseudotactylites in general are very underreported because they're so easy to miss. And they can tell you lots of cool stuff about the tectonic history of an area. So here's a scanning electron backscattered image of the same material. And so I don't know if you guys are that familiar with the way scanning electron microscopes and backscattered electron images work, but basically the grayscale here is how dense the material is in terms of atomic density. And so the denser it is, the better it is at bouncing electrons from the rastering beam back at a detector. And so things that are typically really bright white are things like magnetites, right? Like iron oxides, that kind of stuff. Because the rest of like the rocks that are like silicates and like aluminum and that sort of stuff, they're not really that dense. So what you see when you look at these things at the real micro scale, you know, that bar there is 10 microns. What you see is like a bunch of quenched textures, right? If not outright glass. Not that you can like see glass that well, but you find these like crazy lathes, right? Indicative of flash quenching, which really makes a lot of sense for most pseudotactylites because, you know, the measured temperatures of these things in experiments are like super, super duper high, but they form these like very thin sheets with huge surface areas against rock that is not 1800 degrees Celsius. And so they tend to quench really, really quickly. And you get these like beautiful sort of like quenched textures in all of the microlights that make them up. So when you see textures like this, right, it's really good indication microstructurally that what you're looking at is a quenched glass. And depending on the environment, that is almost certainly going to be a pseudotactylite that you're looking at. So now we're going to go back to that picture from the very beginning and look at our field zone. So zoom way out, and you're going to be in the far, farther northern edge of Saskatchewan, which is this one. I don't know if you can see my mouse or not, but you drive there. It's like a solid 3-day drive from Denver in your truck, and the last 700 kilometers of which are ice roads, which in the summer are terribly exciting because lumber trucks come barreling down them at like 60 kilometers an hour. And there's basically no humans for like most of that 700 kilometers to get there. But this is in the Western Canadian Shield. It is a massive, massive exposure of the lower continental crust in 3 distinct domains. We're not going to get too much into like the different domains, although all 3 of them are absolutely fascinating. What we care about is the ductile structures that juxtapose these big metamorphic terrains together. And so the one that we care about the most is the one with a little sort of outlined box here that joins this domain up here called the Northwestern domain, imaginatively, with the Chipman domain. The picture I showed you at the very beginning was the Chipman domain, which is a very like tonalitic and like anorthosite sort of rock. And the Northwestern domain tends to be dominated by quartz-rich sort of granitic lithologies. That's going to be important later, but for right now, we're just looking at the connection between them, which is the Cora Lake Shear Zone. So we're going to zoom in on that. And so here's a much smaller field scale map with the lithologies actually colorized. And again, it doesn't really matter that you know what the lithologies are, beyond which understanding that the blue sort of half of this is much more mafic than the sort of northwestern side of it. And so this structure of the Cora Lake Shear Zone has been dated through synkinematic monazites and other sort of constraints to be about 1.8 GA. Long dead, long dead. When you do thermobarometry to the various mineral assemblages that are participating in its ductile structure, it's really deep and it's really hot. So this is granulite facies, which is, making reasonable assumptions about the crust. It's 26 to 36 kilometers down, 700 to 800 degrees Celsius. And just at this one exposure is 4 to 6 kilometers wide as an identifiable ductile structure, and at least 70 kilometers long before it gets truncated by other stuff. So it is like a big lower crustal ductile feature. And so a little example of what this is probably comparable to in a modern day setting would be the Alton Tog Fault, except way low in it. And definitely below the Catfish Range. So, all right. So in case people here are not so familiar with what a ductile shear zone is, got a couple of cool little examples from all around the shear zone, right? So here you have this continuous deformation of this nice little like Riddell sort of orientation of structure. And you can see from the quarter there that it's not very big. I mean, it's like probably a meter or less. And it just sort of like slices through that. And so you can see cool examples of this all over the place with ductile deformation. Here's another one that is a clast that is being recrystallized and broken up and stretched out into its own plane. And you can see it has a particular shear sense that matches what the overall shear zone displacement is, which is strike slip and sinistral. If you zoom in on not the big, ugly, nasty, retrogressed black thing, but rather that sort of nice pink little dude that's on the left-hand side just underneath the quarter, you look more carefully at it, you can see it's also sort of getting recrystallized and like stretched out through the plastic deformation processes. And so here is a cross-polarized light micrograph of that same exact clast as it recrystallizes. And so here you can see the growth of like new grains as that bigger sort of single clast is being broken down by dislocation movement through it. And it's recrystallizing out into these long tails. And you can see that the rock around it is made up of these much finer sort of recrystallized grains as everything just sort of flows plastically. So going back to here's a proper field map that we made over a couple of campaigns up here. And I didn't map all of these things by a long shot. A lot of people have been working up here because it's a really, really cool area. And so building on all the work from the last 20 years or so, I focused my field work on just these pseudotachylites that had been noticed, but no one had ever really like investigated them in this otherwise very hot, very ductile shear zone. And so a lot of the pseudotachylites that I worked with that you can find in this area, they tend to focus in that one sort of ellipse that is dark red colored there. And so the point of this slide is mostly to show you that there's like a lot of field data that was built on to do this overall analysis, because we're going to get into the whole history of the shear zone in order to explain these pseudotachylites. Okay, so the Cora Lake Shear Zone pseudotachylites specifically tend to be hosted by really like pretty mafic stuff, honestly, like very quartz poor and tons of plagioclase. That'll make more sense later, but it's an important observation now. And then lots and lots of these little veins of pseudotachylite have actually been subsequently plastically deformed and metamorphically recrystallized, which is what really prompted a lot of this study to begin with, because that's such a cool thing. And so if you look at this example, right, you clearly have multiple generations of pseudotachylite because everything is undergoing the same sort of flow at the same time. But the younger one isn't as deformed as the older one. And the older one is like rapidly just blending into the overall foliation of the host rock, but you can still distinguish it. And so one of the really cool, interesting, immediate things you can learn here is that there are multiple generations of these frictional melts that have been progressively overprinted by deformation and, as it turns out, metamorphic mineral growth as well. Here's another example. The little injection vein that I told you is normally like orthogonal to the sheet of melt has been tipped in a sinistral sort of deformation sense, and the pseudotachylite itself has a foliation, other than just the clasts that are left in it. So again, you have evidence that this brittle feature has been metamorphically and ductily altered. So this leads us to the first question, right? Let's not fool ourselves. Is the pseudotachylite actually from the same time as the ductile shear zone and not something that happened later and just overprinted it? So we're going to take a little journey into petrology to answer this question. Here's a full thin section, and you can see that there's like some pretty obvious pseudotachyllites, but the closer you look, there's a lot of really interesting stuff happening here. You can see that the pseudotachyllites themselves are sort of cut by various features. And when you look at them really carefully, you can identify 4 different generations of pseudotacholites in this one thin section alone. So we're going to zoom in and look at this guy right here, where you have lots of them sort of all in one little spot. And here, this is so cool, right? So this is a manganese K-alpha map from an electron microprobe. You could try doing this with an EDS. Maybe you've got a really good EDS, you could do this too, but really the probe is where this thing shined. Because manganese tends to concentrate in garnets. So this is basically a garnet map, right? For all the little the little bright spots. And so you can see that you have these like different populations of garnet size that correspond really nicely with the microstructural cross-cutting relationships. And so you can get the sense from here, sort of the different ages of the metamorphic, or the different sort of lengths of exposure to the metamorphic conditions that is garnet promoting, that each of these microgenerations of pseudotacholites were exposed to. And so then here's some more of these backscatter images showing you the mineralogy, showing different examples of the microstructures of a quote, pristine, right? So like a really, really late stage pseudotacholite with progressively more and more overprinted pseudotacholites. And you can see they develop their own foliation, and the mineralogy evolves into something that basically matches the granulite facies mythology around it, which is really cool. So when you do thermobarometry to these teensy tiny little grains through some electron microprobe wizardry that I can only thank Julian Allah at ETH for helping me sort of work through, because doing thermobarometry on really teensy grains has all sorts of weird, fun caveats that you have to think about, but you can do it. You can't do thermobarometry to a traditional quenched, like a fully quenched, like very, very fresh pseudotacholite, because it's a quench process, and so it's not equilibrium, right? So you can't, like, it's not in equilibrium, and so you can't make all the assumptions you have to make to get PT out of stuff like this. But when it's been reworked significantly, you can assume that it is re-equilibrated. And so when you look at the exchange of, iron and magnesium or whatever between the different minerals in the pseudotacholite, it can be reliably interpreted to tell you something about the pressure and temperature conditions that it got equilibrated at. And so when you do this to the metamorphosed pseudotacholite, it exactly matches what the PT conditions were for the shear zone itself. So great, right? Between the overprinting of the textures and the mineralogy, and then the compositions of those minerals telling you PT conditions, you've got a pretty strong argument that the pseudotacholite occurred at the same time, or at least some of it did, as the ductile deformation that you're seeing that was lower crustal. So we've answered our first question, right? Did it form syn kinematically with the ductile shear zone? The evidence points to yes, right? For all the reasons I just said. So we can say, right, the generation of pseudotacholite as a brittle feature was active during lower crustal plastic deformation when it should not have been, and that it was cyclic and presumably long-lived because we see so many generations of it happening in such different states of overprint. So not only did you break the rules, you broke them repeatedly. Okay, so that has brought us through this path of our investigation. So we have the deep conditions of the rupture. So the next one is, okay, fine, right? So we've got this anomaly. We are sure that it's an anomaly. So now let's try and figure out what's it doing down there. And so we're going to investigate this by looking at the shear zone as a ductile feature a little more carefully. So again, when you go back and do a literature review, right, we're not just standing on here, waving a flag by ourselves. There's actually like quite a bit of like pseudotacholite that has been identified in various sort of ductile environments that really should not be where they are based on this general understanding of the brittle ductile transition in the crust. And, when you read all these papers, they're really interesting and they're really fascinating, but like there's not really a clear consensus, I think even now, although I'm 2 years out of the game, about like how you actually get these deep pseudotacholites, when they shouldn't be there. So again, it's like a question worth investigating. So we're going to look at the rheology of the shear zone. And so going back to our little map scale, just briefly, right? Here's just a reminder. We have this like really strong boundary that strikes like this across the map. And then you have all of your little anomalies that are concentrated in a specific part of this map too on that boundary. So just a quick review to like ductile deformation, if this is not something folks think about a whole lot. Ductile deformation is due to like crystal lattice processes, like dislocations moving to crystal lattices, but it spreads out at like huge scales. And so you can understand map scale patterns in ductile deformation by looking at micron scale patterns in crystals and linking them all through microstructures and macroscale structures. So we needed a way of like really digging into the microstructure of this shear zone in order to understand the macrostructure at the map scale. So we used one of the coolest things you can do with any electron microscope, and that is electron backscatter diffraction. So here is the same cross-polarized light image that I showed you before, which probably everyone is familiar with because we all had to do petrology at some point. And here is the exact same area of that slide that was polished to within an inch of its life. And then you diffract a bunch of electrons through it by tilting it at a really high angle to the beam in the scanning electron microscope. And then the beam will hit the crystal that has been polished super, super well, and it will diffract through the lattice. And you take a picture of the diffraction pattern. And you can do this really, really fast and in really, really large numbers. And so you end up with these maps, right? Like this one below you, showing you the orientation of the crystal lattice in like a really tiny spot. I mean, like sub-micron area. And you can get, 500,000 measurements in 5 hours by stepping the beam 3 microns and measuring at each point where the crystal lattice was pointing. And so in our case, this is simplified because it's all potassium feldspar recrystallizing here. But the color scale that you see has black lines for like a normal, what you'd consider a grain boundary, red lines for a low angle grain boundary or a subgrain. And then the blue to green scale is showing you how misoriented, what the difference in orientation is between that spot on the crystal and what the mean orientation of that whole crystal was, right? So you're seeing like the warping of the crystal lattice away from like the general orientation of the grain due to the activity of dislocations and crystal plastic deformation. And so one of the ways we're going to look at this sort of orientation information is by looking at standards, which is everybody's favorite thing, I'm sure. But it's not so bad. It's not so bad, right? So it's a pole figure. So just imagine that there's like a bowl in the plane of the screen right now, right? And what you're seeing here is the 010 plane, which doesn't matter if you know what that is or not, but it's a plane. And so what you're seeing are the poles to that plane being plotted on the inside of this hemisphere. And it's sort of, what it's showing you is that there's sort of a slight tilt to this, but it's, it's basically coming in out of the screen at like a little bit of an angle. And so it's showing you that the planes are all very strongly aligned because those are contours of density, of occurrence density, basically, right? So a bunch of your 010 planes are all sharing a certain sort of orientation, which is super cool. And it's exactly what you would expect for crystal plastic deformation, which is going to exploit like the best slip systems that it possibly can for that particular mineral. They're all going to get on the same page and they're all going to sort of end up oriented the same way, so that dislocations can proceed most easily. So tying that back into like the overall sort of theory of how dislocations move on slip systems, you need a plane for them to be moving on, and then you need a direction for them to be going in. And so when you relate this back to the overall shear zone kinematics, you find that you have particular slip planes and slip directions that are really well aligned generally with the overall sense of plastic movement in the shear zone. And so that's probably the slip system that this particular mineral was using in order to accomplish this ductile deformation. So that's why like the EBSD is a really, really useful tool, but it's also really good at measuring grain size, which we're going to get to in a second. So here's our map view again, right? This has sort of a subvertical strike slip sinistral foliation. And so again, when you take these pole figures telling you the orientations of the different minerals that are participating in the deformation, you can sort of superimpose them on the map scale structures and be like, oh, okay, that makes sense, right? Like these minerals are all showing signs of the same sort of deformation orientations, which is not always so straightforward with different minerals because I like to do all sorts of screwy things. But in this case, with plagioclase and case bar, it's generally pretty easy to understand. So that's how we link the microscale to the macro scale of orientations. So then the last thing we use this for is grain size, right? Because we're not going to like sit here and point count in a microscope for 1,000,000 hours or whatever, and produce like a totally unreproducible data set anyways. We're going to do this quantitatively using the EBSD to get the grain sizes to like a really, really excruciatingly statistically rigorous degree. And then we're going to use experimental deformation data to correlate the grain size with the differential stresses that the rock experience, right? And I'm sure we're all pretty comfortable qualitatively saying that like in a ductile environment, if the grain size is super tiny, it probably is like a higher stress part of that shear zone than a part where the grain size is really chunky. And so this is basically just being able to quantify this a little more reliably. And so here's the qualitative version of the microstructural observations you might make if you were out on these outcrops, where there's a big chunk of this shear zone that is, a quote myelinite, which is not remarkably small, whatever that means to the person observing it. And then there's a big chunk where most people would be like, oh yeah, that's an ultramyelinite, whatever that means, right? It's just smaller than whatever I'm comparing it to in my head. But you do have this like reproducible sort of association of like, well, the grain size does seem to get real small right near this boundary in the core of the shear zone. And that's also where the pseudotactylite was. So maybe we can get some mileage out of that observation. So what you can do then is you can go and look at like the two major mineralogies of either half of the shear zone, one of which is plagioclase. And so here's an example of a myelinitic plagioclase and an ultramyelinitic plagioclase. And instead of having to use finger quotes and like just scowl at your undergrad when they don't agree with you with that qualitative assessment in the field, you can be like, no, look, the mean grain size is definitely much larger in the myelinitic part, right? And it's way smaller in the ultramyelinitic part. And when we apply piezometric sort of calculations to it, the flow stresses, the differential stresses in like the ultramyelinitic part of the shear zone are way higher, which makes sense for a lot of reasons. And so now you have numbers to compare. And you can play the same game with quartz, right? Quartz being the more classic version. And what you see is like, thank God, numbers that like vaguely agree with each other, where despite the fact that the quartz is actually like really, really small, it shows roughly the same magnitude of flow stresses that the plagioclase is telling you it experienced as well. So it's a nice little vote of confidence that this piezometry is not just like total nonsense. Not that you'd hear that from me. And you can also look at these the pole figures and get a sense for what slip systems were being activated. But we're not really going to talk about that, so don't stress out if you don't know what a 112.0 is. Okay, so that's all well and good, right? But wouldn't be a proper geology study if we didn't do like a real transect. So that's what we're going to do. We're going to take a bunch of samples from across this whole shear zone. We're going to measure the dickens out of them with the EBSD, and then we're going to make a really cool cross section. And so here's what we get. Note that none of these are like normal distributions. They're all log normal distributions, which is why they're asymmetric. But what you can see is that the grain size through the myelinitic section to the north and to the south of the core all pretty well agrees with each other until you get to the high strain core, and then basically both quartz and plagioclase just like plummet into a much, much finer grained domain than you do outside of the core. And especially where the pseudotachylites are, when you're measuring the stuff right next to the pseudotachylites, not right next, within a few inches of it, you get some really, really fine-grained stuff. So this observation of like grain size reduction, probably correlating to higher differential stresses, bears out when you do like a really rigorous sort of field measurement of it all. And so now we're going to get back to the real important part about all these lithologies, right? Which is that one is quartz dominated and one is plagioclase dominated. And that ends up mattering a lot. So we're going to end up, sort of summarizing our grain size study with like, all right, low stresses-ish out in the myelinitic parts of this shear zone, but then really high stresses right in the core, which also corresponds to this domain boundary where the lithologies do a major flip from being really plagioclase rich to being really quartz rich. And on top of all that, we have our smoking gun, which is this super weird mechanical behavior happening right where these stresses get super high. So we can take all of this stuff and be like, okay, we have evidence now that like based on the distribution of stresses in this shear zone, we have reason to believe that there is something weird happening in the core that might at some point lead to something anomalous like these pseudotachylites forming. And so the next step then is to apply some experimental ductile flow laws based on our observations to see if we can't calculate how and why this is happening. So this sort of leads us to the question of why, right? Shear zones are often like quite homogeneous, across their width, because you're sort of spreading out the deformation ductily over a very large area, as opposed to like the very, very narrow part of the brittle, crustal scale shear zone model. And so this is an attempt to explain our anomalously high stresses. And so this plot, I probably should have taken this plot out, but this is basically summarizing how flow laws work that are experimentally determined. And so what it's saying is, assuming that you're in the dislocation creep regime and not diffusion creep, and I'm not going to go into the difference between the two because we're mostly dislocation creep in this project. As you increase temperature, which is these bars going down, the viscosity goes down at a certain strain rate. And so this is really a mathy and complicated way of saying, like, as temperature increases, rocks get easier and easier to squish. They flow more readily, right, at different strain rates. And so this is important because you can mathematically model all this stuff. And we did it. And so the last little piece that we needed to really do this like proper full rheological model of the viscosity of our shear zone over its lifespan, we need to know the temperature, right? It's easy enough to be like, look, there's garnets, look, there's CPX, look, there's whatever, right? Like must have been at least degrees. But we can actually do better here because of all the work that's been done in this particular area. And so the thermal history of this shear zone can be pretty well constrained by showing that, like, there's this whole set of like mafic dikes that is a fascinating, crazy thing all in itself that predated this shear zone by not that much, that just like turned everything into mush. Like not much, but it just cooked the dickens out of this whole region, all these like mafic dikes everywhere. And so the temperature everywhere just went really, really, really high. And so then we have a timing for the start and end of our shear zone based on the synkinematic monazite, which is another really cool thing that I'm not going to talk about here. And so you can see, that the assemblage of the shear zone that was stable during deformation, like it changes a little bit, but it basically exists in a range that suggests the shear zone operated, between like 545 and like a little less than 800-ish for most of its history. And then we have another data point a little farther down the timeline where we know that the whole area cooled to a solid like 400 degrees or so. So we have this like really, really high temperature event, and then deformation starts, and then it sort of just cools rapidly throughout deformation. And this is really important because thanks to those squirrely flow laws that I'm not going to explain much more, you can basically say, okay, look, when this shear zone started deforming, the whole region was quite hot, right? And the difference in viscosity between the plagioclase-rich wall and the quartz-rich wall was not that much. 2 orders of magnitude. Who cares? That's like water and warm honey, right? That's like not a big deal at all. But then as time kept going, right, and the temperature pulse from those mafic dikes waned and waned and waned, towards the later stages of this shear zone's history, the contrast between both halves of the shear zone became extreme, essentially, right? So by the mid to late stages of the shear zone's activity, the viscosity contrast was closer to water and peanut butter. And so that is not like a happy ductile deforming situation. And so this is an effect that has been talked about for quite a while, and it's really cool to see it in action, which is basically, right, if you have like a ductile environment and everything is, continuously deforming, when you have huge viscosity contrasts, you create like really strong local perturbations in stress, right? Positive perturbations in stress, because you've got a squishy thing touching a thing that is not nearly as squishy, but they've got to flow past each other. And so you end up with this concentration right at the boundary. So that ends up being our best explanation for why you end up with super high stresses right on the domain contact between the plagioclase-rich half of the shear zone and the quartz-rich half of the shear zone, and maybe why you get your pseudotacholites there. Because if your stresses are high enough, rock's going to break, right? Or it's way more likely to break. So this is summarizing all of that. I think that major lithological contrast in our shear zone ends up being a really, really important thing to think about for why we end up with the patterns of stress and grain size and deformation mechanisms we see in the shear zone. And I think that allows the formation of pseudotacholite in otherwise a very, very hot, very deep ductile environment that should not allow brittle failure at all. But this creates the conditions necessary for you to get these brittle failures. So, last question. Not very many slides, don't worry. So we started off talking about all this seismicity that a bunch of like seismology nerds were saying was happening, maybe down in the lower crust. So what? Did we link back to that or what? So here we're at. We're almost all the way through. Now we got to zoom out a little bit more and think about crustal scale faults in general. So here we are, back to our lovely little cartoon. So, the Cora Lake Shear Zone on this cartoon is like basically off of the cartoon entirely, with any reasonable estimate for how deep it was. And with how long it is on the surface and how wide it is right now, I mean, there's every reason to think that like this had like a brittle shear zone on top of it that was at least 70 kilometers long. And so when we think about that, and we think about a little bit of the work that has been done that tries to correlate the thickness of pseudotactylite with a moment magnitude, you end up with like these are little events, assuming that you can even make that assumption in the first place. But they did this in Italy as well, on a beautifully exposed thing in the Alps. But the idea is, right, like unless your pseudotactylites are like, massively thick, then they're showing you like really small moment magnitude events, which also kind of makes sense in this setting. And that, a lot of this like deep seismicity that is observed seismically is not like magnitude sevens going off at like 30 kilometers, right? It's like a magnitude 7 going off at 5 kilometers or 10 kilometers or something, somewhere where it should be. But then if you look carefully, you can see all these little aftershocks that will sort of crackle off much deeper than they really should be based on these generalizations. And so it sort of makes sense to me, and feel free to fight me on this, that like, this is a big shear zone that was the ductile root, mostly ductile root of like a really big whopping fault system, strike slip fault system, was probably able to pop off some pretty significant seismicity using totally normal, totally legit, brittle failure in the upper crust. But that when you have really, really strongly, like really, really high stress parts of the otherwise ductile lower crust root beneath it, that like that movement, that seismicity could probably trigger like little like aftershocks all throughout the lower crust where you have these points of already very, very high stress. So my preferred interpretation, and there's like a couple interpretations floating around out there for why you get these deep pseudotactylites, is that they're aftershocks, right? Because there's no reason to believe that these are like really, really big earthquakes that you're seeing here. They look like little earthquakes. And so the idea of an aftershock happening in a really high stress part of an otherwise ductile system made more sense to me than any other nonsense that I heard. Oh, including Jonathan Timms. Oh, that guy. So anyways, seismicity lower crust. There we go. We did it. We found it. It's up there. It's 1.8 billion years old, but it's probably happening everywhere. And then a couple spin-offs that came out of this, because I think this was a job talk at one point, was we did a whole bunch of study on the seismic anisotropy of these like big crystal plastic shear zones, because like as you saw, all the minerals end up pointing a particular way when you deform them like this. And when those things are micas, then like you can see these ductile shear zones looking at the seismic anisotropy of them, which is cool to be able to image a ductile structure. And then the work that actually got me the job that I do now was using neural networks to predict crystallographic orientations, because you end up with these like massive data sets of millions and millions of measurements that you can then train all sorts of cool machine learning processes on. So here's a thank you slide to all my compatriots at the University of Massachusetts and the University of Colorado at Boulder that made this possible. And that's it. I feel like I talked really fast. How did I do? 12:43. Nailed it.
All right, that's great. If anybody has any questions, we can have you put them in the chat box, or I think if you
I will need a certificate.
Yeah. So the certificates, they'll be provided to the AIPG CEU certificate to those that stayed on the entire webinar. For the New York, we'll put the link for the quiz in the chat. It'll be available for 30 minutes, so until 1/2 and you can take it multiple times to be able to pass. You have to get 70% or greater to get the CEU certificate for the New York CEUs. But if we have any questions, and I think we can unmute people if they want to raise their hand so we know you have a question, so you can ask.
Oh, raise hand.
Ask a question if you don't want to type it up. Oh yeah, like John did. John did.
Yes.
Yeah. Go ahead, John.
Can you hear me?
Yes.
Yeah, Phil, I noticed at the very beginning, your plot of where deep earthquakes occurred, and it seems that I noticed two areas with very deep earthquakes. One was the Tian Shan, which I know something about, and the other was the Indian subcontinent. And in the Tian Shan is very dominantly strike slip faults in it at the level of exposure we have now. There's compressional tectonics on each side, but the core is strike slip faulting, and India, of course, is being pushed down into the mantle, and so it would have probably a lower temperatures at great depth. Are either of those significant factors in increasing the likelihood of these very deep earthquakes?
I would say yes, for sure.
Yeah.
Yeah,
So,
I mean, I feel, it is a bit misleading that I put this up originally, but I could find better examples. But I think the big takeaway with this study is that, the conditions to find these little ruptures is like not that uncommon, right? I mean, like a rheological contrast, forming a ductile shear zone is, I think, more the rule than the exception. That you have like one weird lithology on one side and one lithology on the other side that tends to produce big kilometer scale shear zones anyways. And so it just might be more common than we thought to create these conditions in the lower crust to allow some amount of seismicity to happen and to find some evidence of brittle failure that then gets overprinted and might sort of confuse the story. And the important thing is to just keep your eye out for it.
Thank you. Yeah. So, somebody's asking about the Georgia Brevard zone. Okay, go for it.
So I think they just want us to probably read it. Any chance we might find PSTS in the Georgia Brevard zone near Atlanta? Suggestions where we might look.
Well, John Salvino, I'm afraid I don't know anything about the Georgia Brevard zone, but you should definitely go look. Look for little like black breccia-y things that are like a couple centimeters thick. You'd be surprised. You can find those things everywhere when you got the eye for it.
Yeah. But the Georgia Brevard zone is a very deep strike slip fault that extends 700 kilometers right through the heart of the very high grade metamorphic rocks of the Appalachians. So yeah, I think that means that probably pretty likely to find these things, right? Bill?
Yeah. I mean, the problem is that they're quite ephemeral, especially if they're in like a really active ductile environment. And so it takes looking quite carefully.
One of the interesting things about the Georgia Brevard zone is that we see ductile deformation in the Paleozoic, I think mainly Paleozoic time, late Paleozoic time. But as the thing got exhumed during Triassic time, it became more brittle as temperatures decreased, which is I found interesting.
Now that I'm not in academia anymore, I can float around one of my favorite like pseudoscience theories that I once heard about pseudotachylites, which is based on one paper that found a bunch of pseudotachylites in the Chiapas Massif in Mexico. And they were doing a paleomag study because the melt and quench theoretically should let you sort of get a sense of the timing based on the paleomag preserved in the frictional melt. And so these were not deep metamorphic ones. They were like normal brittle zone ones. I remember it was so interesting because they did like 15 pseudotachylites and a bunch of them gave like workable results. They were like, oh yeah, okay, we can interpret this. Like this makes sense based on the timing of tectonics, whatever in the region. But then a couple of them basically looked as if they had been hit by lightning, in terms of like the nonsense reading that they were getting out of it. But they were in like a valley, so that didn't make any sense. And so they managed to like sort of, a speaker I once heard, who was a good geologist, sort of tied it in as potential evidence for like the co-seismic electrical current that like may or may not be a real thing. But I always love that.
Yeah. I have another question. Just looking at your maps in gross detail, your sense of movement you're showing as left lateral, but some of the offsets look like they would have been very, very much compressional bends in a left lateral environment. And so you can see them here, the green band here. If it's a left lateral, this is a very the bend just above your 4 to 6 kilometers of ductile shear. That's a very compressional bend there. And that presumably that would increase the likelihood of some of these after effects.
Mm-hmm.
Yeah.
Yeah, I mean, take that map in with a grain of salt because of the field conditions.
Okay. Okay. Mhm. Any more questions? Any more questions from anybody? No. So I think we
All right. Well, Phil, thank you. We really appreciate you presenting for us. Would it be possible we could get the presentation in PDF so we could post it to the members only portion of our website for our members' resources? That'd be awesome. We'd appreciate that. And we'll be getting the recording up on our AIPG YouTube channel, and then we'll promote that as well. So we really appreciate you taking the time to present for us today.
Well, thanks for giving me the time. I really enjoyed going through this with y'all.
All right.
Phil, thank you very much indeed. And thank you to everybody that listened. And thanks for the questions.
Yeah, have a great day.
And thank you, Wendy and Kathy, for putting this all on.
You're welcome.
Okay.
All right. Take care.